change its state. So when it changes its state, the y-axis is temperature, it will remain constant. So if you're absorbing heat while it maintains constant temperature, this is because the potential energy is changing to do the phase change, right? Phase change is associated with changing potential energy. So since the kinetic energy component is constant, temperature, which is a measure of the average kinetic energy, will stay constant. This graph will not look like that if it's ideal gas. Ideal gas will just keep changing temperature because ideal gas got no phase change. But only the molecular forces you can't become solid. Right? It just remains as gas, gassy thing throughout. So you should be able to identify what the different parts are. The gas cools, temperature changes. The gas condenses into a liquid. Then the liquid cools, losing temperature. Then you reach this point where you solidify, right? The liquid changes into solid, and then you lose temperature as the solid cools down further until you get to absolute zero, which is the coldest and object can get. So what are X and Y? Boiling point, melting point. Okay. Then the question says which feature of the graph indicate that latent heat of vaporization? So which is latent heat of vaporization? Is the phase change from liquid to gas. Right? And latent heat of diffusion is from solid to liquid. Right? So that's S. So the question is asking which feature of the graph indicates that the latent heat of vaporization is larger than the latent heat of fusion? So you can make some assumptions. Like for example, the rate of heat lost to the surrounding is constant. Right? Then the amount of time will be proportional to the amount of heat received. So this is why I say that even MCQ question might not need to write some whole thing, because there are some assumptions that the structured question will ask you, right? Or you know what's one assumption that you will make? You will answer. Assume the H, the rate of heat loss is constant. Would you expect it to be exactly the same? Well, it depends on the heat capacity. So we can actually derive it. So when it's follow-up question, like right, Sean, once you're done with the question, I was going to ask you all, what do you think the gradient PQ, P, R, and T, the gradient of the graph here, what do you think it represents? So you use Q equals to MC delta theta because this is actually the period where temperature is changing, right? It's not latent heat, it is specific heat. Then after that, we differentiate this with respect to time. So you get dq dt, which is rate of heat loss to the environment. So we are supposed to assume this is constant because we don't let it work. Then this mass doesn't change, specific heat doesn't change. So we got mc d theta dt, which is the gradient of the graph. Right? So the gradient of the graph is actually h over mc. So it's proportional to 1 over the heat capacity of the object. So the steeper it is, the smaller the heat capacity. Now, let's go check. Right, so Rachel's trusty hockey stick, I'm going to just take and use it again. So we're going to compare the gradient of the graphs, right? You can see that P, this gradient, let's compare with R. Oh no, R is actually less steep. So therefore, we can say that the specific heat capacity of the liquid is actually larger than the specific heat capacity of the gas. Right? And then after that, we go down here and then you see that the liquid is actually seems to be less steep than the solid. So the liquid also still has a higher heat capacity than the solid. So in terms of heat capacity, the liquid is the most, followed by the solid and the gas. Right, so there's a lot of things you can conclude from this graph. There's a lot of information hidden in a temperature time graph. What's that? H is just the rate of heat loss to the environment. So like you put any object that is different temperature from the environment, it's not in thermal equilibrium, then it will lose heat to the environment over time. If the rate at which heat loss is constant, then we can let H be constant. So this is a big assumption though, because usually the rate of heat loss is not constant. The rate of heat loss is somehow dependent on temperature difference. If like your temperature is very different from the environment, you get heat at a faster rate in the environment. Right? Because it's about random collisions. You have more slow moving particles, you on the net get more energy that you lose by collisions to other particles. Right? So actually this is not a very good assumption. In fact, as temperature reaches the temperature of the surroundings, which is probably very cold because it keeps decreasing, right? Then the rate of heat loss should actually be decreasing. H should decrease over time in this question. By right now. Okay, sorry, I know this is just one simple MCQ question that we discussed in like 10 minutes, right? But there's a lot of information in the graph, that's why you have to see it, people identify. And it's not like I'm teaching you all new things because I'm only using Q equals to ML, which you know from secondary school work. Q equals to MC theta from secondary school work, right? Nothing new here at all. It's just asking you to find out what the gradient of the graph is. So the answer should be C. Control C. Right? The length of line Q is greater than the length of line S. Okay, but answering a structured question, you will do some working and then make some statements. speed like? Who thinks it's the same? Who thinks it's different? Who thinks it's different? Different speed. 2, 3, 4. Who thinks it's speed? Then the rest of you never said don't know. Ethan don't know. Huh? Different. You said? What's temperature a measure of? Average energy of particles, right? That's question 1. Now, when you change from water to water vapor, does the mass of an individual particle change? Alright? So, if the average kinetic energy remains the same, and the mass remains the same, then the speed should remain the same as well, right? So the speed is actually the same. It's just that for the gas molecules, the speed can move around the entire gas, and for the liquid molecules, they can only move around the liquid. Okay? So, what if it's a solid? That is very much troublesome, right? What about solid at 30 degrees? Let's say I have a substance that has liquid and solid and can have liquid and solid at the same temperature. That's enormous. Oh wait, no, we can. Okay, let's say we had a liquid and a solid at the same temperature. Do they have the same speed? Who thinks yes? But solid don't have speed. They start in like this bonds.
The vibrational speed.
The vibrational velocity is 0. They cannot rotate solid line, they start in like this bonds. But the kinetic energy of the vibration will be the kinetic energy of the translation of the liquid and gas molecules. Right? It's just that for solid they can't translate. So they will all be vibrational energy only. So this one no, for liquid same, for gas same. This one no speed, or solid particles can't have speed. But they have the same KE field because temperature is a measure of the average KE. It's proportional in fact. For gases we have the equation for it. Okay? Then what about the pattern of movement? That's a weird question, right? So for the gases, you know they move independently. Throughout the gas. And if you refer to your notes, for the liquid, right, they move in clusters throughout the liquid. As your teacher in secondary school showed you triple point of water tomorrow. Triple point of water. Heard of it? No. Hey, I want to look at this is my class. No, it's not triple point of water. Okay, you know, water boils. Water boils into water vapor, right? So what the heck is wrong with this question? How is it water and water vapor can be at 30 degrees? Don't know. The explanation. Ask ChatGPT. Okay, cool. Okay, so let's look at triple point of water. Yes, Megan, just please wrap up. We can write to any email and anything. it's like my second tab now because I use it to write my emails. I think a lot of time, you just write my comment and say, convert this into an email, then you have to order, dear whatever, yeah, very nice, very hot. Then I was doing research for like 5 yesterday, right? Yesterday we were doing a basic task, right? So we focused on this. After the what some topic that we can talk about is addition. Please use it, it's an ultra good useful tool. Anywho, what I wanted to show you is this. This. So this is a sealed container. Now in this sealed container, right, water is boiling into water vapor. Okay, but the water vapor is also simultaneously condensing into water at an equilibrium rate. So that means these two things are happening at the same time in this chamber at equal rate, so that the total amount of water vapor and water remains constant at any time. Also, the water is freezing at some parts into ice, and some ice is also melting into water. Then I'm wondering what the heck is going on, right? All these things happen at different temperatures. So there exists this point, this particular temperature slightly above 0 degrees called the triple point of water. Okay, the reason why it can exist, right, is because of this. Now, this is a pressure, temperature axis. Okay. So of course, this is like 0 degrees, and our room temperature is like somewhere here, I guess. So the water is a liquid. And this is pressure. We are at somewhere like 1 atmospheric pressure. So if you want to have phase change, right, you start from like very, very cold. You start with water as ice. That's something you're familiar with, right? And then your ice, as you increase in temperature, your ice warms up. And then you reach this boundary. This red line tells you there will be phase change. So you start getting temperature, you start doing later heat of fusion, yeah, to melt the ice into water. Then once the ice becomes water, you can increase temperature again, and then the water will start to do phase change into water vapor. And this for us at room temperature and pressure is 100 degrees centigrade. Then you just get gas at whatever temperature you want to get. However, things change a lot when the atmospheric pressure changes. So let's consider a very low pressure environment. In a very low pressure environment, right, the ice will encounter a phase change into vapor. Have you heard what this process is called? Heard of it before? Sublimation. So this graph, right, is for water. Our atmospheric pressure is here. So that's why we see liquid water. But if you live in a very low pressure environment, like very, very high up in the atmospheric pressure is low, any ice that is heated up will become water vapor straight away without having an ice, without having a water phase. Yeah? So think about it. Water is very important for life to do all our biological processes because it flows around, and yet it doesn't escape and go all over the place. Right? So life can only exist, right, within this range of pressure and temperature. So it's like a guide to try to find life in other worlds, astrobiology. So basically what we do is, hey, we're looking at environments way different from Earth's regular environment and see how substances behave. Right? What else to know? There is a point where the phase change lines all meet. And this means that at that particular pressure, which means the chamber that I showed you just now in the photo for the video for the triple point of water, that's not atmospheric pressure. So you can't get triple point of water at atmospheric pressure. You need to seal it in a pressurized container and reduce the pressure to 0.06 atmospheres. And at 0.01 degrees C, you will have the water, ice, and carbon dioxide, the water, ice, and water vapor existing in equilibrium together. That's called triple point of water. So many substances have a triple point. Okay? Yep. Okay. Anyway, if this is water, let's take a look at carbon dioxide too. This is for carbon dioxide, right? It's different because of when it has this triple point. At atmospheric pressure, this is 1 atmosphere somewhere. Because this is 5 atmospheres. So this is 1 atmosphere. our atmospheric pressure. Carbon dioxide sublimates. Have you ever seen dry ice before? My birthday cake, ice cream birthday cake, when it comes to dry ice. Right? It's just solid carbon dioxide that sublimates. But if you increase the pressure, let's say you want a very massive planet with very, very high atmospheric pressure, then you got liquid carbon dioxide. Then how will that affect the biology of organisms, right? Because they can drink carbon dioxide. Carbon dioxide can be part of their will compete with certain processes in the body. Like if I'm not wrong, you cannot have too much carbon dioxide, right? Because I don't know, I'm not a bio student, but there's a field of study called astrobiology. It's lots of physics as well. We need to understand how additional environmental changes affect biological processes. So I'm not too sure, but those of you with some bio background, you can imagine if carbon dioxide was liquid, would it affect the biology of organisms? Would, right? Probably liquid carbon dioxide. Yeah. So it's just that it's not that carbon dioxide sublimates, it's that carbon dioxide sublimates at our atmospheric pressure. But at higher pressures, the carbon dioxide does have a liquid phase. Pretty interesting, right? That's liquid carbon dioxide. Not 100% sure, but I think it's when a fluid behaves like a gas, because that's what it says, right? Okay, you keep these answers can be quite technical, but let's see. Okay, it doesn't have a distinct liquid and gas phase. So they are able to dissolve things easily. And then the physical properties can be controlled because the pressure, small changes in pressure or temperature cause large change in density. So there are supercritical fluids in atmospheres of gas, right? Because they mass a lot, so the pressure very high. Oh, it's interesting. Supercritical water is found on Earth in the hydrothermal vents. So it's like one of the places where they hypothesized that life could develop independently from surface life. And under the sea at very, very high pressures, there are like those volcanic vents that hold oxygen. They have different gas combinations, mostly like hydrogen sulfide, things like that from the volcanic processes. Then they have found bacterial colonies there. Yeah, so their biology is totally different from the rest of Earth biology on the surface because that needs oxygen function. Like we're all aerobic creatures. Yeah, even the plants, our plants are aerobic creatures. They breathe so to speak. Right? They do photosynthesis, but they also need oxygen. Right? Yeah. Okay. Wow. How do I remember that? They respirate. You know lungs, right? It's just gas exchange. No matter what, that's what I haven't done in a very long time. Oh, that's to I think bio. I think primary school is other things. I think bio. Right, so very interesting, right? But this exists, so maybe it is a substitute for organic solvent. Interesting. We use it to make decaffeination. It makes a coffee, but that for no caffeine. Then the properties are between that of the gas and the liquid. So that means like gas and liquid behave very differently at our atmospheric pressure. And there comes a point where they behave very similarly and then we call it a supercritical fluid. Yeah. You can see that there are certain temperature and pressure ranges where you never get any gas and liquid, right? Because the pressure is so high that you want the molecules to move around, they also can't move around. They're stuck so close together that the intermolecular forces fix them in the lattice. And that's like ridiculously high pressure, like 10,000 pascals. And we don't have that on the surface, but you have that in the cores of all the planets and stars, right? So the gases behave very differently. And so the kind of physics that we are exposed to of all the substances is just like one tiny slice of the universe. There's like lots of exotic physics that exist in different environments in the universe. Like in the stars on the surface, right, there's gas, but it's so much energy that the gas have all the electrons stripped out. Not just ionized, but super ionized. Ionized to the point where all the electrons are free electrons. Right? Then we call that plasma basically. It's a soup of electrons and ions. So it's very different from our breathable oxygen atmosphere. Not only are there no diatomic molecules because there's so much energy that the ones spontaneously break, but even the electrons all come out. Because enough energy for the environment to come out. First ionization, second ionization energy, all ionization energy, right? The environment gives you enough energy to fully ionize all your atoms, no molecules. Molecules can't form when there's too much energy. So very exotic environment. So what kind of physics goes on there? Very different from the kind of physics that permits life here. Any little bit of magnetic field, things will start moving because there are particles. Okay, so very cool, right? Phase diagram. So this is the PT diagram, right? That actually tells you about phase change, right? And phase change is not a fixed thing. So actually you have done this before. It's just that you didn't see the graph. Your secondary school teacher probably taught you something like when you go up a mountain, the boiling point of water changes. So like you can't get 100 degrees water. You can only get like 80 degrees water because after 80 degrees it boils off. So actually this graph tells you that, right? At lower pressure, the phase change is at lower temperature. Right? So that's why when you go up the mountain, the pressure is lower. It's easier to boil things. Okay, wow. That's extra fun stuff. Let's finish up the question. State by step the internal energy of the system is the sum of the molecular Ke and Pe of a substance. Okay, at last, use your answer in B where the sum to compare the internal energy for unit mass of water and water vapor at the same temperature. So also do it for the solid, okay? Let's do it for the solid. Now, we'll do sum of Ke first. Same. And oops. Speed, right? Speed, movement, and now Ke. So all of them have the same amount of Ke at the same temperature. How about Pe though? Who has the most Pe? Gas has the most Pe? The most? Which one has the most intermolecular forces? Solid. So should solid have the most Pe? Yes? Is that what you want to answer? Solid have the technically have the most Pe, have to shift up. Let's try and case it. You're right. Who has the most Pe? Liquid or gas? You wrote it before. So it has more internal energy. You're right, liquid. Water has more internal energy. You wrote water has more internal energy. Whoever wrote water has more internal energy. Okay. Let's recall a topic that we have learned last year that is similar to intermolecular forces. Which topic? Which force have you learned that is similar to intermolecular forces? You got don't have that? Gravitational force. Why? Intermolecular forces are attractive forces. Gravitational force is an attractive force. What's the sign of gravitational potential energy? It's always negative, right? Attractive forces give you negative potential energy. In chemistry terms, you want to break the bond, you need to give energy. So that's why the energy it has is negative. So for solid, the Pe is most negative, less negative, and least negative. So who has the most internal energy, which is the sum of these two things? It's the gas, because of the negative sign of internal of potential energy. So the gas has the most internal energy. Liquids, because it has more intermolecular forces, hence having more negative potential energy, has slightly less, and the solid one is the least. Now it makes sense, right? If you think about it. If I have very negative internal energy and I want to do the phase change, and then we give solid the most energy. Right? That's like in the least. Yeah, so that I know that it's a kind of pop-up. Who wrote that gases have the least internal energy and saw the negative potential energy by only one person? You can't even see that, did it? Ideas? Cannot do it.
So I'm a bit lost, I can't like.
Lost about what?
A little bit, it's just like I don't finish the SI.
Okay, internal energy is sum of Ke and Pe. So if K and P are both positive numbers, right, then whichever has the largest will become the most, right? But internal potential energy is actually a negative quantity to obtain for attractive forces. Okay, and this is good, right? Because all of us are HB students here. The next topic that we're going to study after thermophysics is electric field. And electric field, there is attraction, but also repulsion. So the potential energy possessed by two like charges is repulsive. They have positive potential energy. Whereas unlike charges behave like gravitation, attractive, then they have negative potential energy. Okay, so let's repeat it. The learning part of this whole question is same temperature, same speed. But potential energy is negative also. So that's two things that you all might not have thought about it. This is question 9, right? Okay, new question. Anyone not done? Still need some time to do corrections. Go ahead. Yeah. Okay, question 10. This is ice melting into water. Even without the circuit turned on, the ice is melting into water already. So, first question is the ice in thermal equilibrium with its surrounding? Who thinks it is? Yes. Who wrote yes? In thermal equilibrium. Anyone wrote no? No? Scott, are you right? You're right, yes. Okay, why? Okay, good answer. Okay, you're wrong. But we want to discuss the logic. Okay, so the Lawrence is trying to make a mistake so that you uncover all our wrong assumptions. So Scott, why do you think is in thermal equilibrium? Is it because I don't think there's no temperature never change? Okay, so that's a true statement, right? The ice temperature never change. Okay, John, did you agree? Ice temperature didn't change. Do you agree? When the ice is melting, right, the ice temperature doesn't change. But thermal equilibrium is not about whether temperature of a substance remains constant. If you look at question 2, thermal equilibrium is two substances must be same temperature. Now, which two substances am I comparing here in question part 1? Ice and surrounding. And they must be different temperature because if not, the ice will not absorb heat from the surrounding to melt into the water. So, according to your assumption was correct, right? Ice really is not changing temperature. So, we're not comparing ice to itself, we're comparing certain object is placed with it. And another way to say it is thermal equilibrium gives you no net heat transfer. But if you don't have heat transfer, ice won't melt. But it will remain as ice. It needs latent heat. So it needs to be transferred latent heat in order for it to melt. So that's how you can answer the question. In case I'll write this down so that everybody can get a comprehensive answer. You assume the negation is true, then you see what's the conclusion. So if you assume that it is in thermal equilibrium, then there will be no heat transfer. If there's no heat transfer, then the ice will not be melting. But the ice is melting, so therefore there is no heat transfer. There is heat transfer and there's no thermal equilibrium. So this is a comprehensive way to answer the question. Okay, back to calculation question. You're going to get the calculation. Let's see how it should look like. Nice. Right, so it's L ice. Then we'll do our substitution. Mass is 114. Later heat time 5 minutes minus 12. So as with most of those heat transfer questions that we did before, question 5 to 7, right? We just apply conservation of energy. See who is losing heat, who is gaining heat. So the ice is gaining the latent heat to melt. The heater and the surroundings are the one losing heat to the ice. So the power of the, instead of doing energy, I'm dividing by time throughout and doing power. Why? Because the question gave me power of the heater already. So I want to go and find the energy of the heater. Right? So the power of the heater plus the rate of heat loss to the environment, okay, is equal to MC delta ML latent heat divided by time. But the time it told us is 5 minutes, so I can do the substitution here. Find the mass of water melted, latent heat of ice minus the power, you can get 14.2 watts. So that's one way to calculate the heat transfer from the surrounding by having a control